Now we're ready for the long announced regularization, section 4.5, regularization and the TSVD. Suppose you're given an operator A with a very large condition number. Then we want kappa of A to become much smaller without having to change the operator A too much, because A is describing the physical properties of our system. Of course, that should still be the same essentially. Of course, that question is very vague, because what means much smaller and what is a little bit? We have to quantify this and we have to answer whether or not we can do this. But let's try to find such an operator B which is close to A and has a much better condition. So let B be this new and improved A. Okay, let's write down the formulas for the condition numbers and let's see what we can do. And let's try this factor by factor. So let's start with the first factor, which is the norm of the operator itself. Can we make that much smaller? I doubt so. Because if A is very close to B in the operator norm, then also norm A and norm B are very close together as real numbers. Convince yourself that this implication is true or ask me in the problem session. Okay, so if we change A only a little, then the first factor will change only a little. So all the hopes and all the pressure now rests on the second factor. We have to get that one a lot smaller by changing the operator only a little bit. And let me ask this question in a positive way. I'm not asking can we, but I'm asking how can we get the norm of the pseudo-inverse below a given bound, let's say 10, by changing the operator A as little as possible. Okay, and that's exactly the right question, which is always good. I mean, asking the right question is often the real way to success. And then you need the right instruments. And in our case, the right instruments turn out to be the singular values of A. So let's try to draw the set of singular values of A, which is of course a subset of the non-negative real axis, and singular values could be pretty much everywhere. Okay, there could even some be at 0, because we are not excluding the case that A is non-invertible, because we're speaking about the pseudo-inverse right away. So in theory, A could be non-invertible. And now the norm of the pseudo-inverse is 1 over the smallest non-zero singular value of A. Let me denote this by S min for simplicity, noting that it's not the minimum because we're ignoring the zeros here. Okay, and now what was our problem? Well, the condition number, which is this product, is too large. And unfortunately, we cannot do much about the first factor, so we have to get the second factor a lot smaller. We blame it all to this factor. This is too large at the moment. So the fact that this number here is too large must mean that S min is too small. It's too close to 0. It wouldn't be a problem at all if it were equal to 0, because we are ignoring all the zeros when we compute the norm of the pseudo-inverse. But non-zero and close to 0, that's a problem. So our question was, can we get this value below 10? And we succeed if we get the smallest non-zero singular value above 0.1, which is 1 over 10. But now suppose 0.1 is here, so this is 1 over 10 on our axis. Then currently the answer is no. And now let's try and construct our new and improved A, which is B, from here. And let's start from its singular values. And the problem with A was that it has very small but non-zero singular values. They are smaller than 1 over 10, which is why the inverse is bigger than 10, or the pseudo-inverse. So we have to get rid of these singular values here. And we just mentioned that it wouldn't be a problem if we replaced them by 0, which is a good idea in at least two ways. One way is, well, 0 doesn't hurt the norm of the inverse, it just doesn't care about zeros, because we only look at the non-zero singular values and take their minimum and then 1 over that. And the second reason is, if we move them to 0, then that means we're not moving them very far, because the problem is these are close to 0. And if you're not moving them very far, then you're not changing the operator very much, and that's the other thing we want to do. So maybe we can combine these two things and find a good solution here. So the idea is to replace all singular values of a that are between 0 and 1 over 10 by zeros. So everything that happens between here and here moves into that point. Okay, and all the other singular values of a you just copy down to b. So we leave the rest as it is, including the singular vectors. Okay, so this part here was just copied down. And now that's your new and improved a. In particular, the norm of the pseudo-inverse, which is still 1 over the smallest non-zero singular value, should now be less than or equal to 10, because your smallest singular value is now here. Your smallest non-zero singular value is now here, above a tenth. And also the difference between the operators a and b shouldn't be large, because the only difference is in very small singular values, which should result in a very small norm. So let's try to write this down generally and well, maybe more proper. So instead of 1 over 10, let's take a little epsilon positive, and then let's start with our operator a, which we decompose into its SVD. And let's suppose the singular values are ordered from large to small in this direction. And in particular, sk is the last that is above epsilon. So everything that comes after sk is less than epsilon. Okay, and then our idea here comes in and transforms this operator a into this other operator. Let's call it b again. And we are not changing the singular vectors. And we are not changing the singular values that are bigger than epsilon, but the ones that are smaller than epsilon, those will be turned into zeros. Before we check that this method is doing its job, let's not forget to give it a name. This is called the truncated singular value decomposition, or in short, TSVD. And let's name this transformation here R as in regularization, TSVD, and of course also the parameter epsilon is playing an important role here and should be mentioned in the notation. Okay, we get that the norm of the pseudo-inverse of b is 1 over the minimal non-zero singular values that survived this truncation procedure. In our notations, this was S1 up to Sk. And by the way we enumerated them, we know that these are all larger or equal to epsilon. So that the result is less than or equal to 1 over epsilon. So epsilon used to be a tenth in our example, and 1 over epsilon is then 10. And now let's see how far a and b are apart. Okay, and because everything was defined in terms of singular values, of course we have to copy this here. Okay, and now because we didn't change u and v star from here to here, we can just regroup this like this. Okay, and then we can compute this new diagonal matrix where lots of entries cancel, which are these ones here, against those. But then what we see here is just the singular value decomposition of A minus B. So the singular vectors from the left and right are still the same, and the singular values have changed a little bit. The large ones have become 0, and the small ones that used to be less than epsilon, they survive this difference here. So the result, the norm of this product is just the norm of this diagonal matrix here, because isometries U and V star do not change the operator norm. And then the norm of that diagonal matrix is just the largest one of its diagonal entries, which is certainly not one of those zeros, but one of these. But they are all less than epsilon, so the result's going to be less than epsilon. So indeed, the parameter epsilon from our truncated SVD here gives you on the one hand how large A and the new and improved A are apart from each other, and on the other hand its reciprocal gives you the size of the new pseudo-inverse. Okay, so maybe let's come back to our example. So to achieve this pseudonorm less than or equal to 10, we have to change our operator by about a tenth. And if we even want to achieve the condition number below 10, we need to make the pseudo-inverse this small, where norm of A is roughly still the same as norm of B. And then when you multiply them, you get the condition number below 10. Okay, but in order to get that, we have to change A by the reciprocal of that number again, which just means it's a tenth of its current norm.